Alright, time for another draft science video presentation. Recording correctly. Okay. So we'll go into some more two slit details. And the details are important. People should notice when something's being glossed over. I'm noticing it in Professor Lewin's presentation. And it's fair game to bring up stuff. So Stephen Bro made some comment about the single, the large spot in the single slit. Okay, the middle node is twice as big, and he says every one he's measured is always 2 times exactly. I'd argue that's not true, but let's accept it as true. We're going to play a Professor Lewin where he's using a variable slit, and you can watch it, and it doesn't really change much. It doesn't swing in and out, as you would expect if the nodes are changing their positions in some sort of dramatic way. But there's a catch. Okay, so there's always there's just the way you have to play the game is that there's real facts and then there's these fake notions. Now, Professor Lewin, I can't find the exact spot where he says it's non-negotiable. Okay, that the center maxima has to be in the middle because the 2 lines are equal distant, blah, blah, blah. And as I've pointed out, well, that's sort of an illusion because those lines are actually going in, they're converging. They can't get larger on the screen. So the node would have to fit in 1 millimeter. A node that might be 5 centimeters in size somehow has to fit inside of 1 millimeter. Can't do that, obviously. And if you do your real geometry, you'll find that it doesn't work. Okay, that if you actually draw the physical lines, you'll find out as soon as you move a little bit, just the tiniest of angle off of that 1 millimeter, you get a different answer. They're no longer in phase, they're out of phase. So the truth is, the fact is there's 2 kinds of diffraction. There's the diffraction that goes in, that obviously has a finite place it can land, right? All the diffraction going in can only land on a finite amount of space, 1 millimeter, where obviously all of the diffraction that goes out, and out means, in the same direction, out, okay? It has an infinite, we're not going to play that game, but it actually has a lot of space it can land on. So it's obviously going to get magnified with distance. So that's just a fact. Now, I don't think anybody's going to dispute that. I don't think Farley or anybody else says that's not true. That, the stuff going in has to land on a finite tiny amount of space, and the stuff going out can land on a whole bunch of space. So that can't be an argument. So I could say what Professor Lewin says. I say that's not negotiable. We shouldn't have any argument about these certain facts. So I'm going to list it, but I'm going to point out some of the certain facts that I pointed out in the other video. So some of it's going to be redundant, and just point out that you can't really argue about these facts. So the implication of these facts are certain things, and you just can't escape those implications. And that's all I want to point out. There's no escaping them. I can't change those facts. You can't change the facts because you agree to them. They're the whole reason why your thing works too, is because of those facts. So there really can't be any room for disagreement on 98% of the argument. And we're really just arguing about a tiny percentage that I would argue is, again, not arguable because you're arguing from an insane position where you're not conceding what's an obvious fact. That the sources they're using are not the centers of the slit. They're not using wave sources. They're using the surfaces as the sources in the single slit. Exactly what I'm arguing. There's not some 2 waves inside of the slit. No, there's a wave on the surface and a wave on the surface. That's the math they're using. So it's obviously my math. It's obviously math completely consistent with my argument. And in the double slit, the simple argument is you have to concede the math that works is also coming from the surfaces. It's not making 2 waves. So again, and now you lose all connection to water and sound because water and sound don't create the same pattern, and the sources aren't in the same location. When you have sound interference, it's not going to be from 4 sources in the 2 opening experiment. Anyway, So I'll play this a little bit just to show one of their gimmicks.
C. Well, it's very different from what you may think. I will plot it now in terms of x. I could have plotted it in terms of theta, but I decided to plot it in terms of x.
And x is really, he's talking about intensity. So he's plotting in terms of x, which is intensity. And he's doing it, so here's the big cheat.
So here, at x equals 0.
Okay, so he creates an x equals 0. Now if he's doing a different experiment, like the double slit, this will be a 1. Okay, this won't be x equals 0. There is no 0. There's a 1 here. So all you're doing is changing the fact that now with a 0 you can put a 1 on either side of it. So now obviously the center will become twice as big because you have a 1 on either side of it. But if you make this a 1, then you're stuck with one node. And then 2 is another node, and then 3 is another node. So just with this little mathematical gimmick, you can change the whole experiment from having a double center to having a single center with a gimmick. But it doesn't work. If you draw the actual lines created, they won't create the big central maxima.
There is unmistakable, unnegotiable, there is a maximum. That is.
So unmistakable, unnegotiable, there's a maximum. So there he's saying it. And you're saying, oh, that's because he's saying, oh, the two lines have to clash. They're two equal distant lines. They have to clash in the center. They're clashing inside a center of 1 millimeter. The center on the screen is still just 1 millimeter of distance. Obviously, a whole node can't fit inside of 1 millimeter. So again, he's using what is Fresnel type diffraction instead of Fronten-Heer diffraction. You know, the two, one of them is for things going in, one of them is for things, rules for things going out. And so it's a detail, but it's a really important detail. So if he actually drew the vectors, there won't be any double maxima in the center. If you actually draw the vectors, it won't work. So if you actually take 2 points, put them on a line, and then draw your vectors, you won't be able to make a double-sized node in the center. It won't work.
That coincides with theta equals 0. And then here, at lambda divided by a, completely destructive interference.
Right. But again, he's arbitrarily placed it, and that's it. So now that he has the 0, he's all set to create the illusion, okay, of the larger central maxima. So anyway, and he's plotting intensity. So listen to this part.
That's that angle theta 1 times L. And then here, L 2 lambda divided by A, complete destructive interference. And the same is true, of course, on the other side. And what you're going to see now in terms of the intensity that I showed you there, watts per square meters.
So watts per square meter, we're just talking about how bright the light is. So he's using the information from the intensity to justify saying, I'm going to put that on the x-axis. I'm going to represent it on the x-axis. And that's, you know, part of the gimmick.
Is a curve that looks like this. Get an enormously broad maximum.
So, and he takes the maximum all the way to where there's total destructive, when obviously it shouldn't go where total destructive is, because total destructive should have as much of the curve as total constructive. So he's just deliberately drawing it poorly. Okay, so anyway, it's not an important detail, but it's a little bit to understanding, you know, the whole story. So let's go to where he's using the variable slit. So
Simply small because A is very large.
So it's wide open now, and all you're getting is the diffraction from the laser's round opening. Now, a feature that isn't explained or isn't stated is that when they do these experiments, these lasers don't produce 528 nanometers or something. There's no exact nanometer of light that you're creating with a laser. You create 7.2, 702, all the way to maybe 745. A whole range of frequencies is created. this is a real problem for LIGO, because LIGO is trying to do something so exact, and they, it's one of their hardest things to do is for them to produce a laser that produces exactly the same frequency. Every photon is exactly 702. That's the tricky part. So that means that this pattern is going to be everything in between. All those different frequencies are the same thing as saying they're different colors. And just like the different colors show up at different locations in different size bars, the photons are creating different size bars in different locations. That explains why, something kind of obvious. So let's just point this out. This is all part of the facts. So we have this idea of constructive interference. All right, and then we have this idea of complete destructive interference. But if we said it the right way, we would say this is where there can be light because the two are in phase. And if we were strict and we said no light that's out of phase could exist, that is, that's all 701 or 702 or whatever the number was, and no other light could possibly hit the surface, then all we'd have is a little line. Right? It's kind of like the lines you get for absorption and reflection spectrum. But there'd just be one tiny little thin line, because that's all that's supposed to be, right? And only that line, because 703 the line would be here, and 715 would be over here. The line moves its location depending on the frequency. So this location is only for one specific frequency. Other frequencies are going to be here, 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 and here, 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 here. Right? And then so if you only had one frequency of light, if it was actually what they're putting in the math just puts one number in, 701. The truth is you're not looking at 701, you're looking at anywhere from 675 to 725. Okay, those are the frequency ranges you're actually looking at. And so they average out to 701. But the photons aren't the average. All right. And so what you would see is line, then you'd see nothing. It's not destructive yet, but it's certainly not constructive, so you have nothing. And then you have nothing. Okay, I can't draw it, right, because it's a zero. But there's a nothing here, okay, where you have complete destructive. But you can't tell the difference between off and not on, right? Not on looks exactly like off. So the pattern you would see is just going to be line, and then there'd be a line here, and then there'd be a line here, and that would be what you'd see, right? Here, you can see that line then. You just see those lines. Because, but so the point is, that's not how the experiment's done. So the real fact is this is what we're really doing, and that means that's why when you see the pattern, the on block is big, and the off blocks, well, it's not in the center, but we'll just pretend it is, and the offs are small. So the ons are much bigger. The node of on is much bigger than the node of off. And you have to make an approximation and say this is really where destructive is starting. Okay, this is really destructive. Okay, and this is the center of constructive. But it's still not right, because you have some light that is, this is where the 642, the 675 light is here, and the 725 is over here. So these lines are all in here. So you can't really argue about position, because the position, there is no center. There's no proper center for the exact math you used. So there's no way to see the differences, because there's no real line for your mathematical number. Your mathematical number is lost in all of this. All right. Yeah, I think that's enough on that part.
But now watch. Now I'm going to tighten to make A smaller. And I'm doing that now. I'm making it smaller and smaller.
Now, see, this would be really great if he did have a single frequency. And see, the problem is even if he had a single frequency, if I'm right, there's no way for it to fix anything because you can still see all the other sub-frequencies. So the 701 could go into the slit, and the slit could be, bending the light all kinds of path lengths that aren't 701, and you'd still see them because they're a new frequency, but it's a new frequency close enough to the original frequency to still be seen. It's still a good frequency. It's not exactly 701, but it's close enough. And so that's what sort of makes it impossible to have the single frequency of light and actually do the experiment and have that frequency stay consistent through the whole experiment. Because as soon as it changes the frequency a little, you're not going to be able to tell the difference between the 706 light and the 701 light. You can't tell the difference between those photons. But the fact is they'll land at a different location.
Fraction which is still negligible, making it smaller. I'm beginning to see the dark.
Yes, he's beginning to see the what is a clear bar pattern. But anyway, let's continue.
Dark lines. The diffraction.
So they look very square until he makes it very big, and then they start getting rounder and rounder. All right, so the central maxima is Stephen Bro says throughout this thing it's exactly 2. I would argue that you can't see the subtle changes that are happening in these sizes, and so I don't think it's always exactly 2, but whatever.
Which is taking over.
So this doesn't look like, this looks like more than 2 of these, you could argue. There's more than 2 across this length. But whatever. I'm just saying it's a subtle argument.
Look at the center maximum.
It's a fair argument to make. Now, in this case, it really looks like more than 2. If I took the measurement of how long this light is, it definitely looks like more than 2 of them could fit inside of here. But again, a more precise experiment would give us more precise results in terms of the exact size of the node. But again, part of the reason we can't see that is because we're getting the whole range of frequencies. Your constructive interference is supposed to be one tiny location. And look, it's spread over a huge location. Constructive is over a huge location compared to the destructive part. You can just see that the brights are so much brighter than the darks. And the only time the darks get larger is because this isn't a curved surface, so the bars are stretching, and the number of photons is getting less and less on the outside. So the dark bands look bigger, but they're not really bigger. Okay, you just have fewer and fewer photons in the constructive part. All right, so play this.
Right there. It's getting wider. It's getting wider. And I make the slit narrower. It's getting wider.
So now it looks like a lot more than 2 of these are in here,
It's getting wider. Look how.
But it's not, it's not like it's going in and out and in and out and in and out. And that's what it sort of should do based on every wavelength of difference you widen the thing through. It should go through a transition. But there's no transition because of the number of frequencies you're using. So if you were using if you could use just one frequency and actually cast just one frequency on the screen, then you'd see that line move its positions. The true center would be moving. And I'll explain why you can know it has to be that way. You really don't have a choice to believe anything else. Okay, so let's do that part, because we've got enough out of this, I think. Alright, so I'll pause and erase and then be back. Alright, so let's go through some of the non-negotiable bits. Okay, so we have a slit. So we're just going to do single slit for now, but like I said, this applies to the double slit, because the double slit really is just 2 single slits, and you just have to add them together properly and you'll get the pattern. Because there is 4 surfaces, not 2. Anyway, alright, so the math is basically just a length. Now it's non-negotiable, let's just argue that the length number in the math can't change. You can't do the math with this number being variable. The length has to be consistent for you to predict the pattern correctly, because the length is integral to understanding the relationship between the frequencies and the image you're casting. So this is the screen you have to view it on. This is what the math predicts. So let me just state it that way. It's non-negotiable that these are the positions where you're going to have constructive and destructive interference, not back here on a infinite screen. Okay, the math isn't predicting the stretched pattern you would end up creating on an infinite plane. It's predicting a pattern here. Okay, so that's non-negotiable. And what you're really doing, okay, what the math is doing quite explicitly, so just remember that L number is always there. Okay, it's a radius. L is a radius, okay, equals R. It's a radius. All right. Now the tricky part is this space here, right? Because we don't have a central point that we're going to draw these lines from. But when they're doing the math, let's just understand that this distance is the distance between the surfaces. It's not the distance between two waves in here, like this or something. Okay, it's right on the surfaces. So it really is the two-wave phenomenon, and the two waves have to be centered on this distance. So that's where the wave centers are. So it's completely consistent with what I'm arguing, because that's where the scatter is happening. All right, that's their math. So that's non-negotiable. You're drawing your vectors from here to here. And so you're doing it to all these points. You can draw vectors. And all you're really looking for is, they use the sine of the angle, okay, the angle difference between the lines. They use this theta to do their math. So they do the theta times the radius to do what they predict. Now, you can do it just by looking at it, and you can just measure it with a ruler. Okay, you could just say, how much longer is this line than this line? And if it's a full wavelength, that is the wavelength of your average light, 701, right? So we know that's just the average. That the fact is that there's a whole bunch of 688 light, and there's a bunch of 722 light. All right, so that's just an average. And the 788 is going to be in a different position than the 722. They're going to be in different places where there'll be a full wavelength. So you understand that I have to move it more this way to get to 722. And I have to go more this way to get to 688. For that to be, this distance to be 688. Right? All right, so we already know that math is just describing a circumstance that doesn't actually exist, because we didn't put all these variables in. And if we did, then we'd say constructive interference happens in this whole range. So because of this range, that's why this is big, is because there's a range here of frequencies that I can see, and that can be made by taking these 2 points, okay, and saying what's going to happen at this location. So the exact half a wavelength off, then you're getting into a much bigger number, right? I mean, if the half wavelength, then you could argue that's like comparing 701 light to 350 light. So that's a big dramatic difference. So all the way off is going to be kind of obvious. So the off is going to be here. Anyway, so you know that this you can't change this. You can't change, this is how the math is done. So that's non-negotiable, right? The math is just vector math. Okay, it's very famous, the triangle they create, the angle they create, the whole thing. That's all known. It's a fact. So you can't change that. All it's about is how many lengths are on this line. That's a wavelength. How many 701s? 701, 701. All right, how many positions can I get to where I have a 701 worth of difference? 701 nanometers worth of difference in that line. All right, so that's all you're doing. So now, as I pointed out in the other video, another non-negotiable thing, that it really isn't up for debate, or it isn't possible for there to be any dispute that we're both talking about the same thing. Okay, you can't turn it into, oh no, your physics is different than my physics. the point would be is this is your opening, these are your 2 points. And the fact is there is a line from this point to, and then a line from this point. Those are real places. This is a real place, okay? In the experiment, this place at 90 degrees is a real place. And you can draw the 2 lines, and the 2 lines are right on top of each other. And you know for an absolute fact what the distance difference on this line is. Okay, it's going to be some multiple of something, right? It's going to, whatever. I can just make up any number. 56,000 nanometers. Okay, but obviously it's probably not going to be that. It's probably going to be something like 56,372 nanometers. And then I have to divide my 701 in there. Now you can understand that, well, if I divide 701, it might come out even, right? I don't know. I mean, I should have picked numbers, I guess, that would make that obvious. But let's just say I put 701 in and I get an even number of exactly 43, let's just say. But if I put in 707, okay, I get 42, well, 707, yeah, that would be more. So that would be 42.6. So I'm getting different, really dramatically different in terms of whole number versus remainder numbers from very subtle changes in the wavelength. So now you can understand where this gets kind of screwy, because it's going to be an off, almost an off, okay, and almost an on, depending on what wavelength of light I'm actually using. But anyway, let's just play this out. So we know that at 90 degrees, this single point isn't just a single point, and I can't even represent it because I really can't go this way, but I have to. So I have to create the artificial idea that the node is somewhere centered in here. So I take the average number again, and that'll tell me what the average thing is doing, and I'm just going to add all the non-average. And so if the average is a 0.5, let's just say it's just an odd number. Okay, so let's just make it 45. So it's a whole number, but it's 45, and half of 45 is going to be 22.5, right? So now that's where it gets tricky, because my center isn't going to be an on. Okay, anyway, so I start with an on, and you could just say that that this is constructive. So for 701, this is the center, okay, and you have a node, just one node, and then the next node is going to be exactly the same size as that node, and then the other one's going to be exactly the same size as that node. So that's something that's non-negotiable, is the fact that the distance you're rolling on this circumference, right? This circumference is just like the same as this line, except we multiply it by pi to get this length. But it's going to do exactly the same thing as these notches. So you're really just taking these notches, this length, and multiplying it by pi to figure out what it is on this circumference, and pi, the radius times pi. The L number that I took out, this number, L. Okay, so that's what you're doing. You're just taking this length, whatever it is, proportional to this total length. So you take this total length, that is the L's, L this way, L that way, find out the proportion of this length to that length, and then you're just going to redo it on this bigger line. You're just going to do exactly the same proportions on this bigger line. You're just going to take this line and put it on this line. And so you have the same notches, the same number of nodes. So whatever nodes you have here, however many wavelengths fit in, that's going to be how many total constructive and destructive nodes you're going to have going across. Now the place it gets tricky is right here in the center, right? Well, anyway, let's just play along. So we know this one's non-negotiable, right? Because the lines are right dead on top of each other. There's absolutely no doubt about what this one has to be. It doesn't have any choice, okay? It's the most solid of solid outcomes is here. So that's non-negotiable. We shouldn't be able to agree or disagree, agree to disagree or any of that horseshit on that. That's as obvious as it can be. The lines are right on top of each other. There's absolutely no error here. This total distance is the wavelength difference. And whatever it says, if it's a whole number, then it's an on. If it's a remainder, it's a heading for off. So depending on how much remainder I have, it just tells me how much I'm heading for off. So if I'm a perfect 5, that means I have complete destructive. So if it's 42.5 wavelengths in here, complete destructive here. And if it's a whole number, complete constructive. And now I'm just going to take those numbers and move them by exact amounts of distance. And up here, you're going to obviously get into some sort of trick, right? Because it's a total on here, but right here at this center, again, if I cut 45 in half, and that's exactly, it will tell me exactly what's here in the center, I got 22.5, so I don't have a whole number anymore. I got an off. A total destructive is right here. So this isn't going to match this, and certainly this doesn't care about this. All right, and so that's the part that messes everything up, is the fact that they haven't realized that this only happens within the 1 millimeter of space. This whole experiment's taking place, it's inside of 1 millimeter. It's less than a millimeter, the whole slit. These two dots are less than a millimeter apart. This internal thing can only happen inside of 1 millimeter, okay? It's a tiny amount of space. It's not the true pattern. The true pattern is up here. The true pattern is doing this. And so this is going to be destructive, which means the constructive is starting here. And the constructive on this side would be on this side. And that's the true pattern. And if you did the math, if you did your real vectors, you would see how this one breaks right away. That all of a sudden, if you did this straight up, 1 millimeter. So understand, this is only a millimeter difference. So this straight line isn't way over here. It's inside of here. Okay, the two lines are little lines right in here. These lines that look far apart are really little tiny lines way in there. And so now your vector difference, just going right outside that 1 millimeter, you could sort of understand that now these two lines are now going the same direction, and there's not going to be barely any difference between them, and blah, 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 and I'm not going to have a wavelength change and all that kind of stuff. So it's going to completely change here. So inside the millimeter, yes, it's constructive, because that's the internal diffraction. But right outside that millimeter, the external diffraction is deciding, and that isn't going to be two equal lines. Right outside this millimeter, it's no longer two equal lines. All right, so I'll try to draw a representation of that. So what's being argued is you have the point sources you can't change, the lines you can't change, and the thing you have to be aware of is that when the two lines are going up, okay, the real question is where do I stop? So this is where I'm comparing two lines, this line versus this line, and I'm going through this whole arc. But there's a point where I stop. This one's going in this direction, and this one has stopped going in this direction, right? So they're both going in the same direction the whole time. But as soon as I get to that point where this one is now going to start turning to go the opposite direction, I know that's where I have to stop, because I'm not going to get accurate results anymore. Because what's happening in here is going to overwhelm. But understand, this is just 1 millimeter of space. So the thing works, okay? Establishing this as your first node, it works all the way up to this point, right up to the wall of that 1 millimeter. But when you get to the wall of that 1 meter, the rules will change, because now your two lines are going into each other, and now you have a different kind of diffraction. But right up to that point, it's fine. So that's the argument, is that whatever is happening on this side is also happening on that side, because they're exactly inverted. So, the same problem happens going this way. It's when this line stops going this way. When you stop going this way with this line, make it straight. And then this line is still going that way, and this line's not. And so, obviously, that's a different kind of diffraction, and you'll have a different number for whether it's constructive or destructive. But anyway, it works all the way right up to that millimeter. So, this distance tells you where you start. You can't change the size of the nodes, so you're stuck with the results all the way up to this point, and it's exactly the same math as your math. We're both agreeing that the math is you just take the distance, okay, divide it by the wavelength, and you're going to make these vectors. We both agree on these lines. This is how I'm deciding. I'm drawing a line with this base. The base is the number of wavelengths, and that will tell me whether this is on or off, on, off, on, off. And there's just no room for disagreement that we're both saying these are all the same positions. Lewin would predict the same thing I'm predicting, okay, for all of these locations, and the only one that's changed is this middle one, and I'm claiming it's a fake one because it's inside of a millimeter. So this isn't automatically an on. This is quite probably an off, and it's quite possibly an off. And all you're doing is saying, well, there's enough fudge, okay, in this on, right? The on-off is so fudgy because all of these, if it was 707, well, then this would be further over. If it was, 6, whatever, so I'm moving them over, and so they're just blending into each other, and I can't see one from the other because the inconsistency of the frequency makes it impossible for me to see the actual constructive interference line, the only one that's supposed to count. The only one that's supposed to count, I can't see it through all the noise of all the ones that are counting they're not supposed to. They're not the actual right frequency, so they started a different than the first one started. So, 701 would start here, 702 would be here, 703 would be down here, 705, they're starting in a different location, and therefore they'll finish at a different location. And so they're just fudging. They're causing a bunch of smear in the constructive node. The constructive node should just be a line, and it's not. And that's what makes it impossible to see the changes that are happening when you change the slit width and you change whether you have a whole number here or not. So you don't see the variability because of the variability. Yeah. Okay. It's lost. The center has been lost because you can't see what frequency light. You can't tell the 688 from the 720. And because you can't tell, you can't see where the real center, that's the wrong way to say it, so I won't say that. But anyway, that's the only, I'm just saying all the way up to this here, all the way up to this 1 millimeter wall, you have to concede there's no room for disagreement. So we're perfectly in agreement on all of these locations right up to that 1 millimeter. And so there's just really no argument about, well, let's argue about how big the center node is. Well, we can't really argue about it because it's already dictated by this node. So why are you arguing about it? It can't possibly be anything else but what it is and what the math says. So it's either, you either have two nodes that are separated and the laser light is obscuring that center, that off, or you have two that are merged into each other. But that's your choices. It's going to be this or this. And the point is you can't see enough of it to tell the difference between this and this, especially because you can't see that the parts that are merging don't have anything to do with the explicit 701 you're supposed to be looking at. And you can't see that. You can't see the 701. So you can't see that this line, this distance is a little bigger than this distance. Yeah, that's the only way to say it. But I'm just saying, if you think it's negotiable that this node can be variable, that whatever this center is, if you think you can start at the center, so if we agree the nodes have to be the same size, there's no way to evade that. The angles force that to be true. The distance on the rope forces that to be true. So you can't evade that. So if you start with a center here, an on, you know that you're going to have this dictated, and it can't be variable. This has to be dictated by this line. These lines are going to dictate that. You can't dispute this, and you're going to force it to be disputed because you're pretending that I can have an odd number of wavelengths here. A non-whole number of wavelengths here, and still have a bright here when you can't. All right. Don't know if there's anything else I need. I'm just saying this isn't the fun part of arguing this. The more fun part is the part where I point out that the double slit, let me just do that for the sake of making the video a little more fun, is that you're just obeying these rules. Rules that we are really not negotiable. We can't change the rules, so these are the rules. And as I pointed out, the double slit just tells you. So let's understand, the single slit really was exactly as I said. The waves have to be at the scatter points, right? And so all you're doing for the double slit is you're sticking another two surfaces inside. So we have to accept that the single slit is still doing the single slit thing. This is where the wave is. And when you do the single impediment, you do the same thing. You count this distance. You count the distance between this surface and this surface. So you're already conceding the point in the sense that you can't really evade that and those are the vectors that work. So when I do the math, that vector arrangement works perfectly. The widest distance will create small on-offs. That's a fact. Okay, the more wavelengths, then the more locations that can be on and off. The smallest distance, as a fact, okay, has to create big bars. Just a fact. And that all you're really doing is saying, yes, we're all four, line up, all four are in phase. I have a bright. That means I got a contribution from this, and I got a contribution from this. That's a bright. When I have a contribution from this, but no contribution from this, it's a dark. And you just keep, and then when I have a contribution from this, but no contribution from this, it's a dark. And so it's just telling you that, yes, this is the pattern. Just take these out. Take these spots out because they won't be visible. And there's your double slit pattern. It's just a superposition of this two surfaces and these two surfaces. You're just putting the two patterns that would be created by those independent experiments. If I did an experiment without the impediment, I'll get a pattern. I take that pattern and then I superimpose on it what I get when I have two tighter surfaces, and then I recognize that, let's say, do it in do one in blue light, do one in red light, and wherever you have purple, the blue and red mixed, that's where you have light. And it'll match the double slit pattern, it'll predict it, it'll do everything you need to do, and it'll do it by your own math. Your own vector math already has that truth in it. And the only thing you change for the double slit is you just have to do your vector math twice. That's all. The double slit, the four source double slit math that works is just basically doing the same math twice. That's all it's doing. It's just doing these two surfaces and these two surfaces, and then it adds them up. And says when are they both in phase, and that's your pattern. That's your on. That's your constructive interference. That's your on node. So it's kind of indisputable that the surfaces are the cause of the effect, that Feynman is not correct. Every single photon takes a different path. No. It's quite obvious that some photons go right straight through, no problem, and some photons don't. And the fringes are made, the ones out here are made out of the photons that don't go through the slit. They get busted by the slit. And all you're doing is putting them back together. It works. It's simple. No superposition. No, the photon went in and turned into two waves. None of that crap. So, yeah. So, again, like I said, there's all kinds of, you have to deal with the actual facts, the actual details. No one's ever explained why the brights are bigger. I'm arguing the brights are bigger because you're not doing one experiment with one frequency of light. You're doing a bunch of experiments with a bunch of frequencies, and it's just spread the pattern all to hell. Okay, that's why. Now the shape thing just has to do with the shape of the laser beam, why they comes out sometimes round. is that the image of the laser is actually getting through the slit. So that can be fixed by getting further and further away in terms of sending your beam to the slit. So the further away you go, the less round the bars will become. Simple things like that. The clearer, more defined the shadow. So, see, it's so easy for people to use lasers and put things close because the laser is so coherent. It's already doing a straight thing pretty well, but it's not doing it that well. And the fact is the further away you get, the more you change the relationship between the distance of the target and the distance of the source. And what you're doing is just recognizing that, yeah, the closer I bring the object to the target, the sharper the shadow gets. The closer I bring it to the source, yeah, it screws up. The shadow gets blurrier and blurrier. So if you want to see it clearer, you have to put the source of the light further and further away. Those kind of rules have to be applied. All right, anyway. So they're all facts. They're all part of understanding the mechanics of the experiment. And I'm just arguing that over the hundreds of years that this has been a phenomenon, since 1801 when, Young announced this special super thingy that wasn't accurate. Let's understand, his math was wrong because he was taking the middle of these. Instead of taking the impediment distance or the surface distance, he was using the middle of the opening as the distance. And you're going to understand that distance isn't going to give you the right answer. That's not going to predict either the envelope or the little bars. It's going to get both of them wrong. So that's why it doesn't work. It isn't reasonable. And even so, all Einstein, Bohr, all these people who discussed this experiment, Feynman, all these people, they never really picked at it. And that's what you should at least be able to acknowledge. They never really said why. Why this, why that, why, and looked for a mechanical explanation for why. They just created gimmicks, like Professor Lewin changing the center line from 1, an on node, to 0. So now he has an excuse to make the first node giant. Those kind of cheats. They just engineered it to work so they could make their wave theory, they could engineer a solution to its obvious failures. But they can't get out of some of them. Just as I pointed out, the two-slit math is using exactly the surfaces. Nobody draws it with two waves coming off the surfaces. Why don't they do it? Because, that doesn't look rational, does it? It doesn't look like the explanation they're looking for. If the single slit's creating two waves, how can the double slit only create two waves? So they never do any rational comparisons. They never ask the questions. The physics is so undercooked. They're so sloppy. They're not following the recipe of science. They're just sitting there and doing it as quick as possible. And with the agenda of proving a point rather than the agenda of let's find the actual truth. They want to prove the theory they believe in. They don't, and support it anyway. They don't want to find the truth. They're not after the truth because they're not asking all the questions the truth seeker would ask. Why is the central maxima twice as big? Why is it shaped? Why is it, why is it so much bigger? Why is the constructive interference blob so big? It shouldn't be. It should be one location where it's in phase. And all the rest of those locations should be some percentage out of phase. And all you're saying is that the dark spots are where it's completely out of phase. That is 90 degrees out of phase, and it gets closer and closer to being back in phase. It's the most you can be out of phase, is at the darkest point. But the rest of those points, why is there light getting there? Why is it creating light when they're supposed to be pretty substantially out of phase? Oh, that's right, because you have lots of different frequencies in the experiment. That's why. All right. So that should be enough of a video. I think that was the half-hour reminder. See, is there anything else I need to add? I don't think so. That's fairly complete. Well, it's a half hour since I enlarged the screen, I guess. It's a half hour since I used the mouse. So yeah, it's a 40-minute video already, right? Yeah, it's plenty of video. 50 minutes, yeah, that's plenty. All right, so it's just a clarification, just pointing out again, there's no room for disagreement about this whole string thing and all that. Those it's not just a gimmick. It gets exactly the same answers your vectors get, and it just makes it a lot easier to see how you can't automatically say it's always constructive at the center, because the fact is it's not always constructive at 90 degrees. If the 90-degree number can change, then the center number has to change. There's no alternative. And the reason why you think it doesn't change is because you're not understanding that your two equal lines only happen in a tiny, 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 minuscule amount of space. And they're not equal really quick. As soon as you get out of that tiny amount of space, they're not equal anymore. Alright, so enough said. And so till the next time and such and so forth and whatnot. Yeah. Oh, I forgot. This has been a DraftScience video presentation. Blah blah. Thank you for your attention. I can say that. And such.